Hi to all the students. Hello everybody. Are you all able to hear me and see me? Let me know. I was actually trying to download this PPT. It was actually a Google slide. I work on Google Slides, and today I have been waiting since 8:55 to download this PPT over here in the screen, and it's not happening. It's not downloading. Ultimately, I had to use my laptops and phones, and I'm trying on all of my devices to download this PPT. Finally, out of all these devices, one of my device was able to download. I think it would be some server problem, and then I have emailed this PPT to me. But anyhow, you'll be getting up a PDF, don't worry. So this is where I was actually taking a lot of time, and I'm so excited to see you guys. But as I told you that everybody has to join the session, maybe 5 minutes before the time, right? None of you did that. I was actually thinking that this is the only reason I am not able to download the PPT. So next time, do join it early, so that probably the PPT can also get downloaded soon. Okay, and in today's class we are going to be starting up a different chapter. This chapter is of class 12th, solutions. But from now, what is so special about these classes, that we are going to complete this chapter in 3 classes. So if you think that you have to revise this particular chapter, it is going to help you. If you're a dropper, it is going to help you. If you're a fresher who's going to give the examination in 2022, it is going to help you. This lecture, I am assuming, is going to be much more longer. Expected on an average, it would be somewhere around 1.5 hours. It can go beyond, it could be less, depending upon your speed. What type of speed? The understanding speed. As soon as I ask you, is it clear? If you have a doubt, let me know. If it is clear to you, let me know, so that we can move forward. So these 3 classes, you can actually take it like solution chapter in 3 shots. But why not 1 shot? Because guys, I'll tell you something. See, 1 shot games are just like giving you something in a very good speed, but nothing can be like complete. So some or the other topics would be left in 1 shot, and that's the reason I'm not giving you 1 shot. Okay, we have time. It's not a damn crash course, and do not fall for one. Let's simply dive into the lecture. Okay, I am going to introduce myself. I am going to introduce Unacademy platform as well for those who are new. And let's start by taking up few names over here. We have Abhirami, we have Vidya, we have Rakesh, we have Khushi, and we have Riya, and we have Vidya, Lakshmi. Amazing. So anyhow, what I can clearly see is that everybody is actually keeping the chat alive. So please start S block. S block is going to happen after periodicity. See, let's go with the flow, because Abhirami, what's going to happen next time, another student will come and he or she will say, so give me this. So I cannot change the flow. But if you need S block, I'll give you in special classes. I actually use special classes like an on-demand class. So if you need S block or maybe 1 shot, I'll give it to you. Okay, so do not worry. And now, for those who are watching me for the first time, my name is Luv Mehan. I am a graduate of IIT Bangalore. I've taught and mentored more than 50,000 plus students. My own All India rank had been 361 in GATE 2017. You should be following me on Unacademy with the username @LuvMehan. And apart from this, do not forget to join my Telegram channel, which is Luv Mehan JEE Chemistry. And there's one more Telegram channel which is right now there in the chat. Do join that Telegram channel, because me and Yava sir, both of us are putting up our sessions in that particular chat, okay, in that particular channel, and you'll be getting updates regarding physics and chemistry, a lot over there. And now, ultimately, you should remember, for 2021 students, if there's anybody, or if you would like to refer somebody, if they want to prepare for 2021 advanced, there is a crash course. Apart from this, guys, 2022 students, coordination compounds, metallurgy, surface chemistry, DNF block elements, electrochemistry, chemical kinetics, solutions, electrochemistry, even solid states. Everything has been covered by me, from past 3 to 4 months on plus. And by the end of the September, we will be completing up the inorganic chemistry of class 12th as well. So if you want to dive into a batch which is already running and keeping each and every class on track and time, then you should definitely come on my plus classes, because I never miss my plus classes, and we are preparing for JEE mains and advanced both. And ultimately there are few more batches which are also going to teach you in English, and ultimately we have a Spark batch for 2023 students. So if you take one subscription, you can actually sit in both the classes. Okay, so do remember that if you want to revise 11th and 12th simultaneously, then you should go for Spark batch and the Shine batch. Shine batch is for 2022 students, droppers and freshers. Both of these students are attending this particular these particular series. And apart from this, if you are aiming for a drop, if there's any student who is aiming for a drop, then something big is coming for you in very few days. So stay tuned. Okay, subscribe to the channel. And ultimately for 2022 students, as a lot of you are 2022 students, remember this: a lot of batches coming up right away, and all of these batches are going to be helpful for droppers and freshers. What do I mean by freshers? Let me know in the chat. You guys should tell me. Okay, if you guys are going to be wrong, I'll let you know. Apart from this, if you are looking for scholarship, I'm talking about 1 year of free Unacademy Plus subscription for JEE, then ultimately your rank should be between 1, 2 or 3. If you need 75%, the ranks 50%, 11 to 50, the 25% rank should be 51 to 150. And in where these ranks should be? These ranks should be achieved in Unacademy Combat, which is the scholarship test. Every Sunday 11 a.m. this happens. This test is absolutely free, and you do have to use the code, which is me actually, Luv Guru, LUVGURU. So do remember this. Okay, droppers means the repeaters actually. Whenever I say freshers, that means you never have given JEE. You are right now in class 12th. You are going to complete your class 12th. Okay, na? So droppers are the ones which are going to repeat, which tried giving 2021 JEE, but they now think that they have to repeat it again. Okay, so do remember that. Yes, the 12th class, 2022 students. Hi Balaji, welcome to the session. And boys and girls, where's the attendance? You guys have to mark the attendance, right? And how do we do that in my class? By hitting up the like button. So do that. Okay, and now ultimately you should remember that what all features do you get on Unacademy Plus and Iconic. So first and the foremost thing, India's best educators. You might be available in any part of this country, but ultimately are good educators available around you? Maybe yes, maybe no, but on Unacademy always a yes. So ultimately you get the India's best educators over here, their live classes. And what's the point of live classes? The doubts. On a recorded class, you cannot ask a doubt, but over here, each and every session and batch is live. And ultimately, you have structured course and PDFs. So you should remember all the courses that you are going to see are structured. What do we mean by structure? That means that ultimately all the sessions, all the lectures are pre-planned, and you will always know when this batch is going to end. And the PDFs, short notes of the teachers are always available. Live test and quizzes happens, so which actually gives you a lot of competitive feeling. But what's more in Iconic, it is about the personal coach. A personal trainer for one particular student. One particular trainer is going to be there who will be looking at your tests, your booklets, your assignments, everything. I mean, they're not going to make assignments for you. They are going to see how are you doing, and how they should, they will be giving you regular advice how you can become better. And ultimately, even I mentor a lot of students. So if you want me to mentor you personally, LUVGURU is the code that you guys have to use. What's the code? And is there anybody else who wants to get mentored by me, wants to achieve the best ranks? Then ultimately, do not forget to use this code whenever you are buying the Unacademy subscription Plus or Iconic. And if you are going to go for Plus, you can actually later upgrade for Iconic as well, no issues. But you should remember, right now, for droppers and 2022 students, I am recommending 12 months. For 2023 students, I am recommending 24 months. And for those who are actually going to go for 2020, 12 months and 24 months, you guys will be getting up the Unacademy's branded notes absolutely free. It's not available for 6 months. It starts from 12 months, 18 or 24 months. So do remember that. Okay? Yes. And now let's ultimately start this class. So today's topic, today's chapter that we are starting up has a name, solution. And we are not just going to talk about solutions, we're going to talk about the colligative properties as well. But to be very honest, we will not be talking about colligative properties today. The whole dedicated class is going to be the next class, where we will be covering up all the colligative properties. And yes, it's going to be a one shot for colligative properties. But today, it's going to be the introduction, the terms and everything. all the basic stuff in one shot, where I am going to be teaching you a lot of formulas from mole concept as well. So ultimately, you're not just going to revise the solution chapter, but also the mole concept. So it's going to be a feature-packed class. Okay. Yes, amazing, Khushi. So now, what all examples do you have whenever we talk about solutions? What all type of solutions are available in around you? So just to give you a kick start, I have an example over here as well. What do you really think, boys and girls? What are they actually drinking? I mean, there are two things which is coming. I won't say about the second one. I'll just talk about the first one. I feel this is lemonade. What do you think would be the second thing that would have come in my mind? It's all because of the color. Okay, but now do not put it on the chat. My bad. Sorry. Okay. So now ultimately they are having lemonade. Correct? Is lemonade a solution? To be very honest, yes. I mean, it has lemon juice, which is consistently mixed. It could have sugar or salt. It is also consistently mixed, and it has water. And a solution can have maybe two components, the water and the lemon juice, right? Or it can have three components, the water, lemon juice and salt. Or it could have four components or more, something like water, juice, salt, sugar. Could there be a fifth? Could there be a fifth component? I can just think about four. Is there anything else that you can think of? What else do you add in Nimbu Pani? Let me know. Okay? And now, so yes, this is what we're going to talk about. Did you hear? I was consistently saying that it is homogeneously mixed. I talked about that it is mixed consistently. Correct? So solution. Whenever we talk about solution, you should remember it's a homogeneous mixture. Do write this. Solution, or we can also write it as true solution. Okay? And when we talk about the heterogeneous mixtures, we have colloids and suspensions. Okay? So colloids. Just today we are not going to talk about colloids. Whenever I am going to start a chapter which is surface chemistry, then we will talk about colloids. But just giving you an example, milk is a colloid. Suspension, sand, mud in water. Okay, so now are we going to discuss heterogeneous mixtures today itself? No, this chapter is not about colloids and suspensions. This particular chapter is all about the solutions. Okay, so do remember that. Okay. Okay, we have students' choice. Hats off to you, bhaiya. You always see very motivated and energetic during classes. Thank you so much. If it is all about me, if I am your bhaiya, or maybe I don't know if you to whom you are referring as bhaiya, I'll take it as a compliment. Thank you. And now over here, what are we going to talk about? True solutions. And true solutions are the homogeneous mixture. What is the most easiest way to define homogeneous mixture? Two or more components mixed consistently. Okay, so do remember that. And apart from this, yes, the definitions are going to be there for you, but do remember this particular chapter is mainly going to talk about the binary solutions. What do we mean by binary solutions? Binary solution means two components like water, alcohol. Yes, water, alcohol. No other example. Okay, benzene, or maybe just two components, HCl, water, anything else. And now when we talk about the ternary solutions, we talk about three components. Quaternary solutions, we talk about four components. But no, we're not going to talk about the three component or the four component systems. Okay, we are only going to talk about the two component system. Okay, and you can have n number of examples, just like juice, the lemon juice, and water as well. And now let's talk about what is a solute and what is a solvent. So guys, I am going to ask you something and you guys have to tell me. Let's say in a container I add 30 ml alcohol, okay, and then I add 60 ml water. So how would you know that which component should be called as solvent or solute? And you should remember that, always remember, solvent is always in higher quantities. solute is always available in lesser quantities. So ultimately in front of you, the lesser quantity material over here that we see is an alcohol. This becomes solute, okay? And whichever is in higher quantity, this becomes the solvent. Clear? Yes or no? The two components. Yes, two components is what we are going to talk about. But yes, 30 ml and 60 ml is what we have to remember, okay? But ultimately you should remember everything has to be homogeneous. Things have to be homogeneous, okay? This should not be like, you know, some components are sitting at one point, you know, point, and or the second component is somewhere else. You cannot call it as a solution if you actually add sugar at the bottom. This is sugar, and here till here it's water. It's not a you know, solution, okay? When you stir it, when you completely dissolve the sugar, then only you will be able to call it as a solution. And solution, whenever we talk about binary system, binary components, we have solute and solvent. Solute is the one which is in lesser quantity, solvent is the one which is there in the higher quantity. Now I'm going to ask you one more thing. Let's say I am having 100 grams of water in which I added 10 grams of sugar. Which one is solvent? Which one of them is a solvent? You guys have to clearly tell me. And everybody, I feel that probably you might be, you know, writing up notes, or maybe just slept. Am I too boring? Let me know in the chat. Guys, be active in the chat, okay? And now, which one of them is going to be a solvent? And the correct answer to this question, obviously, which is going to be in higher quantity. Yes, Khushi is absolutely right. Water is the correct answer, okay? So do remember that. And now you should also remember, whenever we actually add solute into the solution, the solute particles that you see, so these small hexagons, so ultimately it should simply get consistently mixed. So do remember that, okay? And now let's have few examples, okay? And we are going to talk about the gaseous solutions. So we are putting up gas in gas. What could be an example? The mixture of oxygen and nitrogen, the air, okay? When we talk about liquid and gas, and by the way, whenever we talk about the gaseous solutions, the solvent is gaseous, okay? So do remember that. So we are actually adding chloroform in a nitrogen gas. So chloroform is going to be in liquid form, nitrogen is the gas, right? Now let's talk about solid in gas. Is it possible? Yes. Whenever we are actually making camphor vaporized in nitrogen gas, doable. So is camphor getting mixed? Obviously, when we are talking about solution, obviously it will be homogeneously mixed, okay? And now when we talk about, okay, no wide awake. Okay, what's happening? Punarvas, what's beam something, I don't know. Okay, now let's talk about the liquid solution. In the case of liquid solution, the solvent is always going to be liquid. So gas in liquid, cold drinks, CO2 in water, soda. Everybody write soda in the chat. And now when we talk about liquid in liquid, ethanol in water. Again, you know, the liquid solvent. Solid in liquid, sugar in water. Easy examples, right? So do remember that. And now ultimately when we talk about gas in solids, liquid in solid, and solid in solid, this is solid solution, okay? So there are going to be examples for you, but the major thing that you have to talk about, and the thing that you have to really remember, that in today's class, in this particular chapter, we are mainly going to deal with the liquid solutions, okay? Either you will be having a component which is going to be gas in liquid, either liquid in liquid, or either solid in liquid, is what you really have to remember. A lot of solids are also the non-volatile, substances. And we will talk about what exactly these non-volatile substances do. In today's class, we are also going to be covering up two major concepts, the Henry's law and the Raoult's law, azeotropic mixtures, and everything. Okay, so do remember that. Now, before we are anyhow getting into those formulas, the first and the foremost thing that we have to do is revise the mole concept formulas as well. Do you remember the mole concept formulas? Let me know. And if no, let's do it. Over here, the first and the foremost one that we are going to talk about is the mass percentage. the mass percentage. It is weight by weight. So whenever we talk about what's the denominator, it is weight. What's numerator? It's weight. But in the denominator, you should remember it is the mass of solution. And when we talk about the numerator, it should be the mass of the component. This could be the mass, you know, this component could be a solute, this component could be a solvent as well. So if I am talking about, guys, pay attention. I have a solution of alcohol in water. Let's do this, where alcohol is there with 20% weight by weight, or water is 80% weight by weight. Can you really guess which one of them is going to be a solvent? Yes. If the mass, percentage is going to be higher for one component, obviously that is going to be, and with a good margin, then ultimately water seems to be the solvent and alcohol becomes the solute over here. This particular mass of the component, it can be the solvent or the solute. Okay, so do remember that. If the percentage comes out to be, let's say, one component is 40%, one component is 60%, then ultimately 60% one is having more mass. So we technically can actually talk about the 60% one is going to be the solvent. Okay, so do remember that. And now let's take a example over here. So if we have a solution which is 10% glucose in water, so what does it really means? So ultimately you should remember, you should always assume as well that this, the solution is of 100 grams, out of which 10% is glucose. So how much gram is it going to be? 10 grams. How much is left? 90 grams. 90 grams water, 10 grams glucose. So do remember that, okay? You always, and whenever you are going to assume 100 grams or 100 ml, it will always be beneficial for you guys. So always remember that. And now let's do a question. Do not run away from the questions, because ultimately in JEE you have to solve questions. Calculate the mass percentage. Mass percentage is always weight by weight of benzene and carbon tetrachloride. If 22 grams of benzene, this is going to be, let's say, mass of component A, and 122 grams of carbon tetrachloride. So what will you do? So the first and the foremost thing that you have to really look for is the mass of the solution. So mass of the solution is going to be mass of A plus mass of B, which is going to be 22 plus 122, which comes out to be 144 grams. Chalo, we now have the denominator. What about the numerator? We are talking about only the mass percentage of benzene, but not the carbon tetrachloride. So when we are going to write mass percentage of C6H6, how is it going to be? It is going to be the mass of the benzene, 22 grams upon 144 grams into 100, because it's the percentage, it's not the fraction, it's the percentage that we are talking about. And now you guys have to give me the answer. 84.7? Seriously? 84.7? I don't think so. Or are you talking about carbon tetrachloride? But anyhow, the correct answer to this question, when we are talking about the mass percentage of benzene, it's 15.28. So do remember that, okay? And when we are talking about the mass percentage of carbon tetrachloride, then what you really have to do is, don't solve this again. I won't do that. You may do it, I won't do that. If I have 15.28, then ultimately mass percentage of CCl4 for me is going to be 100 minus 15.28. Whatever the answer is going to be, that's going to be my answer. Cool? Yes. Or even if you can actually, you wrote it for CCl4. Okay, I was expecting the answer for the benzene, but yes, good. Full marks to Khushi. Everybody, I'm talking to you as well. Are you guys doing it? Let me know in the chat. How many of you were able to solve this? You can take few more seconds, but were you on the correct track? Let me know in the chat. Now, let's talk about the volume percentage. And whenever we talk about the volume percentage, guys, always remember in the denominator it is always going to be the volume of solution, just the same way it was the mass of solution. And when we talk about the numerator, it is going to be the volume of the component, either solute or solvent. And now pay attention. Acha, by the way, guys, also remember, if 122 gram is CCl4, then ultimately that's the solvent and benzene becomes the solute. So do remember that as well. And now, if you're talking about 10% of ethanol solution in water, so now what will you do? If I have 100 ml of solution, 10% of it, which is going to be 10 ml, is going to be ethanol, and rest 90 ml is going to be water. Clear? Is this really clear? And the total amount, the total volume of the solution is going to be the 100 ml. Okay? Yes. Amazing. Now let's talk about mass by volume. And what is the difference? You will always see weight, which is mass, by volume percentage given in the question. So remember, the volume is going to be for the solution and the weight is going to be for the solute. And when do we use these things? Whenever we have a solute or solvent as liquid, just like water, and when we have the solute as solid, sugar, salt, whatever, weight of the solute. So do remember that, okay? And now, if I am going to have, let's say, 100 ml of water, okay, and now ultimately if we have the weight of the solute and I am just adding 2 grams of NaCl, the common salt. Now what will you write? Over here, NaCl weight by volume percentage is going to be 2 upon 100 into 100, 2% weight by volume is how you can write. Okay, so do remember that. Yes, clear? Amazing. Now let's talk about the parts per million. I'll tell you something. Parts per million, to understand parts per million, it could be confusing. But the most easiest way to remember parts per million is, do remember this. 1 ppm is equals to 1 milligram per liter. And why did I write this? Pay attention. So if I say 1 milligram is the solute and 1 liter is the complete solution. Okay, so do remember that. Okay, so now can I say this 1 liter is going to be water? I can say that, right? Because anyhow this 1 mg in water, again there's no going to be much change in the volume, correct? So now pay attention. 1 liter can be written as 1000 ml. And 1000 ml of water, weighs 1000 grams. Okay, and 1000 grams in milligrams, how much is it going to be? I'm writing 1000 for 1000 into 10 raised power 3 milligrams. How much total milligrams are we talking about? I am writing it as 10 raised power 6 milligrams. Okay, now let's do it again. This is the parts of the solution, okay, or the solvent, and this is the part of the solute, the component. ppm is, over here you guys are going to write 1 upon 10 raised power 6 into 10 raised power 6, and what is going to be your answer? 1. What is going to be the unit? 1 ppm. So now I'm going to make it a bit more easier for you. No, I'll make it slightly tough, but still easier. Now pay attention. If I say 5 milligram of fluorine is available in 1 liter water, what is going to be the concentration of fluorine in ppm? It's very easy. I told you 1 milligram per liter is 1 ppm. 5 milligrams in 1 liter is going to be 5 ppm. So do remember that. It's that easy. But the point, we only use ppm as the concentration, only when the amount of solute that we are adding is extremely small. Even it could be mg, or it could be even nanograms as well. Whenever we talk about nanograms, we get into ppb, parts per billion. Okay, yes. And do remember, we have an example at the bottom. So if we have a liter of seawater, so seawater has a lot of dissolved salts and a lot of things. So ultimately 1 liter of seawater is not equals to 1000 grams. Okay, it is slightly more. How much is it? 1030. Okay, so this is going to be our 1030 grams. Can I write it as 1030 into 10 raised power 3 milligrams? I can write this. This is going to be the parts of the solution. And now pay attention, in which we have just added 6 into 10 raised per minus 3 grams of O2. How much grams? 6 into 10 raised per minus 3. So 6 into 10 raised per minus 3 grams can be written as 6 into 10 raised per minus 3 into 10 raised per 3 milligrams. Okay, we can write this. And now what we are going to do is, whenever we are going to talk about ppm, what you guys are going to write, it's going to be 6 milligrams upon 1030 into 10 raised per 3. That's how you guys are going to do it. Okay, and ultimately you guys get the answer, which is going to be 5.8. Achha, by the way, we just have to multiply it by 10 raised per 6 as well. You guys are going to get the answer 5.8 ppm. But I am taking you till milligrams. Even if you can divide 6 into 10 raised per minus 3 with 10, 1030, even you'll get the same answer. But do not forget to multiply it by 10 raised per 6. Okay, so you can try to keep the unit same. If you are converting the parts of the solution in milligrams, convert the same. These units should be same. Okay, or you can go with the grams and grams. Do remember that. Okay, amazing. Chalo, and now let's move ahead, boys and girls. Is the ppm clear to each and everybody? Now I'm gonna ask you one thing. Let's play a bit. So if I'm actually having, let's say, 10 milligrams in 0.5 anything, okay, 10 milligrams of solute in 0.5 liter of water. Let me know the answer in ppb. I didn't teach you ppb, okay? But I'll tell you something. Okay, 1 ppb is equals to 10 raised per minus 3 ppm, or I can write 10 raised per 3 ppm is going to be equals to, 1 ppm is going to be 1000 ppb. 1000. So let's see how many of you can do this. Come on. So over here, first of all, at least calculate this in ppm, then only you will be able to give me an answer in ppb. So if it is 10 milligrams in 0.5 liters, I can write it as 1 liter, but I'll make it as 20 milligrams. Okay, 20 milligrams in 1 liter of water, it is going to give me the ppm value, which is going to be 20 ppm. And now you have to give me this answer in ppb. 1 ppm is 1000 ppb. 20 ppm is going to be equals to 20 into 10 raised power 3 ppb. So do remember this. Okay, or you can just write 20,000 ppb. Clear? Yes or no? And guys, put some smileys. And where is Abhirami and all the other students? Let me know in the chat. And now let's move ahead. Okay, now we are talking about the mole fraction. So in the case of mole fraction for any component, so what is the symbol for mole fraction? it's more like an X, but like this is called as chi, chi, okay, of any component A. So I'm talking about binary system where there is component A and component B, two components, okay. So whenever we have to know the mole fraction of A, the formula is number of moles of A upon total number of moles of A plus number of moles of B. Do remember this. And what is the formula of moles? How to calculate moles? N value is given weight upon molar mass. Cool. So even for Na, even for Nb, the formula is same. Given weight of this component upon the molar mass of the component. And then what is the mole fraction? Mole fraction of A, if it is number of moles of A upon number of moles of A plus number of moles of B. If I'm trying to calculate the mole fraction of B, then it is going to be number of moles of B upon total number of moles. Do write this down in your notebook. Okay. And now we have a question. Calculate the mole fraction of ethylene glycol. The formula is given to you as C2H6O2. In a solution containing 20% C2H6O2 by mass. By mass, 20%. So now guys, what will you do? Assume we have 100 grams of solution. 20% of this is 20 grams. What are we having over here? C2H6O2. Okay. And now what is remaining? 80 grams. Is it given the aqueous solution? If not, if it is not given to you, if the information about the second component is not given to you, take it as water. Okay. And now pay attention. Let's calculate the molar mass of this one. So it's going to be 12 into 2 plus 1 into 6 plus twice into 16. This becomes 32, this becomes 6, this becomes 24. 24 plus 6, which is 30, 30 plus 32, which comes 62. Right, 62 grams per mole. And now what are we having more? So we are having 80 grams of water as well. Can we calculate the moles over here? I'm keeping this as A, I'm keeping this as B, okay? Number of moles of A, given weight 80, molar mass 18. For this one, given weight 20 upon 62. These are the two things that we actually have to calculate. And then what are we trying to calculate? The mole fraction. And how is it going to be? Number of moles of B upon number of moles of A plus number of moles of B. So you guys have to give me an answer. Stop just looking at what I am doing. Start doing it by your own as well. Moles of water 4.44, moles of B 0.32. Amazing. And then what is going to, how to calculate the answer? 0.32 divided by 4.44 plus 0.32. Okay, so anyhow, yes, let's see. Over here, the mole fraction comes out to be 0.068 for the ethylene glycol, and for the water, it's going to be, I am not going to do it this way. Do remember one thing. Mole fraction of any component can have a range from 0 to 1. Okay. And do remember one more thing, that whenever we talk about two components, mole fraction of B is always equals to 1 minus mole fraction of A. So if you calculate one mole fraction, just simply subtract it from 1. So 1 minus 0.068 is going to be 0.932 is going to be the correct answer. Is this clear? Come on, boys and girls. Let me know. And now over here, let's talk about the molarity. We're talking about the molarity M. It's very super duper important to remember the formula of molarity and molality in this chapter. So we denote molarity by capital M, and the formula is very simple. In the denominator you have to write, because the denominator is very important, volume of solution in liters only. Guys, if the volume is given to you in ml, you have to convert this into liters. And on the top numerator, it's the number of moles of solute. Or in the denominator, it's not solvent, it's solution. So do remember this. Okay. And now when we are going to talk about the question, calculate the molarity of a solution containing 5 grams of NaOH and 450 ml of solution. First and the foremost thing, is the volume for the solution in liters? No. Do that. 450 ml is going to be 0.45 liters. Correct? If this would have been 500 ml, it would be half liter. So if it is 450 ml, 0.45 liters. And now when we are going to talk about the number of moles, do we have number of moles? No. Can we calculate this? Yes. 5 gram is the given weight. Number of moles is going to be 5 grams upon the molar mass. So NaOH has a molar mass of 40 grams per mole. Correct? Now for the molarity, number of moles 5 upon 40 upon 0.45, and that's going to be your answer. The correct answer to this question, come on boys and girls, let me know. Everybody, yes or no? Are you guys doing it? You just have to do this. See, 5 upon 40, which becomes 1 by 8, and then you just have to divide it by 0.45. Acha, anyhow, if the denominator is less than 1, then ultimately your exact answer, yes, over here, the correct answer to this question is going to be 0.277 or 0.278 molar. Okay, so even Khushi was exactly right. You don't have to remove your message. Okay, so boys and girls, for those who are actually able to write it clearly, give me a smile in the chat, because over here Khushi, Punarvas, Riya, everybody is right. So come on, you know, self appreciation is more required. And now let's talk about molality. Molality is denoted by small m, and the formula which can be written over here is going to be same. The numerator is going to be same. The denominator is the only key thing that you have to remember. So that's the reason I'm going to write the denominator first. It is going to be the mass of, not the solution, it's the solvent. And what about the numerator? It's the same. Number of moles of solute. Clear? It's the same thing. Only the denominator is having mass, and mass not in grams. Mass in kgs. So do remember this. Clear? Yes or no? Let me know. And now over here we'll do a question. Calculate molality, small m, of 2.5. That's how you should read a question. Okay, whatever I do, you should read the question in such a form, because you should exactly know what is the question talking about. When 2.5 grams of ethanoic acid, the formula is given to you, in 75 grams of benzene. Guys, this is 2.5. This is 75. Which is a solvent? The benzene. So is it in kilograms? Nope. 75 grams is going to be 75 into 10 raised power minus 3 kilograms. Do it there itself. And now, do we have the number of moles of the solute? So let's do it. So anyhow, it's 12 into 2, because there are two carbons. Then we have 4 hydrogens, 4 into 1, and then we have 2 oxygens. the answer that you guys are going to get is going to be 60 grams per mole. Okay, and now how much is it? This is the given weight. Number of moles comes out to be 2.5 upon 60. That's the number of moles. What about molality? Molality comes out to be 2.5 divided by 60 divided by 75 into 10 raised per minus 3. And you guys have to give me an answer. 0.55 moles per kilogram. Okay, I'm having an answer over here. The correct answer to this question, yes, 0.55 moles per kilogram. That is going to be the correct answer. Amazing, amazing. Ria, you just have to do it again. Okay, don't worry. But yes, guys, hit the like button to mark the attendance, and let's now move ahead. Over here, we're going to talk about solubility. Till now, you have actually, learned and revised all the different types of formulas for concentration. And now we're going to talk about solubility. Whenever we talk about solubility, it means how much substance, how much solute you have added, and that particular solute has gone dissolved. How much solute is soluble in some quantity, given quantity of, let's say, solvent, water, at a particular temperature. So temperature has to be constant. So first of all, the foremost thing, keep temperature constant, and then see how much grams of solute have you added in a given quantity of solvent, and this all amount which is there in grams or whatever, it is completely dissolved, it is soluble. That is going to be solubility. So you should remember this. Acha, I'll ask you one more thing. Whenever we increase or decrease temperature, does the solubility changes? Let me know. I mean, if you're trying to dissolve salt in 10 degrees Celsius water, the water that you have directly got it from a refrigerator, or maybe if you're trying to dissolve salt, the same amount of salt in the same quantity of water, when that particular water is boiling, or which is on the gas when you're cooking, in which scenario where do you think the solubility of salt is going to be much better? The answers should be there in the chat. Okay, so yeah, solubility of a substance which is going to be obviously solute is its maximum amount that can be dissolved. How much maximum quantity you can put in a specific amount of 1 liter, 2 liter, or whatever quantity of water, solvent, at a specific temperature, specified temperature that should be constant. Okay, when we change constant this temperature, the solubility changes. Yes, in the boiling water, in the hot water, the solubility is going to be more for the salt. In a cold water, it is going to be less, right? So now, this is what you should remember. And now we're talking about the solubility of gas in liquid. Okay, this is slightly different, because whenever we increase the gas, whenever we increase the temperature, what exactly happens? Now I'm going to ask you something. So let's say you have a container where you are actually putting up any of your favorite soft drink. You can name it in the chat as well. But now guys, let me know, if this particular cold drink has been poured in this container, plate like or spread like container. Right now the cold drink is at 10 degrees Celsius, which is directly out from the refrigerator. Do you see fizzing? If you see Appy, if you see Pepsi, Coca-Cola, Thumbs Up, Fanta, Limca, whatever, do you see bubbling, the bubbles coming out? It happens, right? But if you are actually going to open up a bottle which is actually not refrigerated, which you directly got it from a shop, and it is not at all refrigerated, and if you pour let's say it's at 30 degrees Celsius. In which scenario do you think that fizzing out, this bubbling, is going to be more? Let me know. You have an option A and you have an option B. In which scenario will you see, more bubbles coming out? Pakka. Do you think? Punarvas is saying 10 degrees Celsius. Anybody else? Come on, let me know. What I really think is I should be giving you an experiment. I mean, I should record it and I should give it to you. I'll do that for sure. I'll make a short video on that. Okay, so you should know the 30 degrees Celsius one will have more bubbling out. Okay, and why is that? Because there's one more thing which is written at the at the label of that particular Coca-Cola or something else. They write serve, tastes best. Yes, tastes best when served chilled. And why do this say so? Because whenever we serve it as chilled, the more CO2 is available in the cold drink. It does not fizz out, and when we drink it, we feel it less sweet. And when we drink a cold drink which is just at 30 degrees 40 degrees Celsius, and if you will try to drink it, the fizzing will be too much more, and as soon as you will drink it, it will be much more sweet. Okay, so that's where if it is very much cooled, CO2 will remain there, and CO2 will overcome the taste of that particular sugar which is available in the cold drink. So do remember that. Okay, yes, but CO2 isn't good for health. Absolutely correct. The pH of the cold drink is somewhere around between it's somewhere between 2 and 3. Okay, and this much pH is absolutely not good for health. So do remember that. Okay, and it's all because of CO2 dissolved in water, because it actually then makes it like carbonic acid inside the soft drink. So do remember that. But anyhow, so solubility of a gas in liquid can be defined as how much ml of CO2 has been added. I'm giving up an example in 1 liter of the soft drink which is made up of water. So how much volume of the gas in how much volume of the solvent, as the volume of the gas which will dissolve in 1 centimeter cube, either in 1 centimeter cube or maybe this is what we are taking it as a unit, because 1 centimeter cube is nothing but 1 ml of the liquid to form a saturated solution, okay, at a particular temperature and pressure. So pressure also plays an important role whenever we talk about the solubility of a gas, because whenever we are actually in industries, let's say this is the Coca-Cola bottle, something like this, hai na? Acha. So now whenever we are actually having the cold drink filled, but till here it's for now it's not having any CO2. What they do is they put too much of pressure and they fill CO2, but with too much of pressure, and as soon as they fill it, they lock it. So whenever you are actually having an unopened bottle of your favorite cold drink, if you would try to press it, it doesn't happen. If you try to press it, it does not happen. It's tight, it's pressure packed. But as soon as you open up the cap, a lot of pressure is released, and fizzing starts. And even you should remember, a cold drink which is locked, which was never opened, a cold drink which is kept at 50 degrees Celsius, the bottle is going to be damn tight. And when we are going to talk about a cold drink which is kept at 10 degrees Celsius, you will still be able to press it. And why is that? Again the same thing, because when we increase temperature, solubility of gas decreases. Higher temperature, more fizzing out is what I'm trying to tell you. Yes? Okay, and now pay attention. So now when we are talking about the solubility of gas, I have told you about the temperature. When you increase temperature, solubility decreases. Effect of pressure. When we put more and more pressure, when we force the gas to get inside the liquid, to get inside the solvent, then ultimately when we increase the pressure, the solubility increases. Okay, and now when we talk about the nature of the gas and the solvent, it talks about what is going to be the interaction between the solvent and the interaction between the gas. So if they love each other, it's going to be amazing. Now I'm going to ask you one more question, one more very amazing question which you can also ask your friends. Now let me know, if you have water 1 liter, and if you have again one more water, one more amount of water, 1 liter amount of water in another container, and if you try to put O2 and NH3, which one is more soluble? Give me a second. This is A. Which gas is more soluble in 1 liter of water? Let's see. Time to be smarty pants. Yes, time to be smarty pants. Which of these gas is more soluble in comparison? O2 in water or NH3 in water? What do you think? Come on, boys and girls, let me know. B. Yes, even fishes, how are they living? It's exactly, oxygen dissolved in water, correct? But no, oxygen is always dissolved in water, it's okay. But the solubility of dissolution of oxygen in water is extremely low. Okay, this is very much high. You can Google it up, do whatever you want. The dissolution of ammonia in water is 1,000 times, nearly 1,000 times much more soluble. This solubility is much more, is 1,000 times more than dissolution or solubility of oxygen in water. Okay, and why is that? I'll tell you. Because you should remember, water is, whenever we talk about water molecule, water is a polar molecule. Water has a polar molecule. Okay, so partially positive, oxygen being electronegative, partially negative. So the net dipole moment over here is the upward one, correct? It has a dipole. But when we talk about O2, no dipole moment. And whenever we talk about a polar solvent, it dissolves polar solute more. Like dissolves like. And over here, NH3, is it a polar solute? Yes. Whenever we talk about NH3, I'm making up the dipole moments. The net dipole moment is again there. Okay. NH3 is a polar molecule, and anyhow, NH3 and water can also show hydrogen bonding. There are dipole interactions, special dipole interactions like hydrogen bonding as well, but with the oxygen and water, nothing. Okay, so do remember that. Though fishes take in O2, but they excrete. Okay, amazing, Khushi. Now, is this really clear to each and everybody? Okay, so just do not believe yourself blindly. If you have less information about the concept, stick to the class till the end. Okay, and now over here, let's move ahead. And now what we are talking about, the nature of the gas and the solvent. Yes, this is what I'm talking about. So guys, oxygen, O2, N2, helium, argon, H2. So these are very less soluble in water. Why? Because water is a polar solvent. And all these three, or these two and these as well, all of these are non-polar gases. So do remember that. And but when we talk about sulfur dioxide, ammonia, these are more soluble in water because sulfur dioxide has a dipole moment, ammonia has a dipole moment, and these SO2 and ammonia, NH3, these two gases have the dipole interactions with water. Okay, not movements, I'm talking about moment. Okay, I'm talking about dipole moments. Okay, dipole moment. So now, not movements. Okay, yes or no? So the gases with dipole moments, it's ammonia and sulfur dioxide, given the example. Even HCl as a gas. Yes, so do remember that. And now let's talk about effect of temperature. You should always remember, whenever we are trying to dissolve a gas with solvent, it gives you solution. Gas is solute, solvent, ultimately solution. But you should remember this particular process exothermic in nature. Whenever a gas is readily soluble in water or the solution, the solvent, it is going to be an exothermic reaction. And ultimately process. Heat is provided. And according to the Le-Chatelier's principle, moving back to the chemical equilibrium in class 11th, if you increase the temperature, if you really allow the heat component to increase, the backward reaction is more favored. The backward reaction is going to be more favored. So do remember that. Clear? Punarvas is saying typo, sir. It's okay. Yes, I totally understand. It's a typo. So is this clear? Even just because of looking at the movements over there, even I said it once, but it's okay. So whenever you try to increase the heat, the temperature, dissolution happens. Gas and solvent will separate apart. And when we are trying to make things cool, when we are trying to make, decrease the heat, make things cool, more and more gas and solvent will try to make solution and heat. So do remember that, okay? Yes. And now ultimately there are some exceptions, but not with the water. I'm not talking about with the water. So whenever we talk about the gases like hydrogen, H2, and inert gases, helium, argon, neon and all, the solubility increases slightly, very slightly, very slightly, negligibly, okay? With the increase in temperature, whenever we are using solvents like hydrocarbons, alcohol or acetones, okay? So do remember that. And now let's talk about the effect of pressure. So let's say this is a container, this is the solution, this is the solvent, okay? The solvent I'm making right now. This is a piston. I'm making up a piston, okay? This is a piston. We are going to exert pressure from the top. We are going to exert the pressure. And what is there between the solvent and the piston? We have gaseous molecules. When we put more and more of pressure, where will these molecules go? Up or down? And what's down? The solvent. So whenever we are going to increase the pressure, these atoms, particles, gaseous particles will start moving and getting inside the solvent. And ultimately, with the increase in pressure, are we going to increase the solubility of a gas? Yes. So do remember that. Okay, yes, they will go down. They will go down, right? So do remember that, boys and girls. So ultimately, if we move the piston by putting up more weight, ultimately when we are increasing weight, we are increasing the force, area remains same. So when we are increasing, A is constant. When we are increasing force, pressure increases, right? So we're increasing the pressure. So what you really see is that the solubility is becoming more, right? So do remember that, okay? Is this clear? And now over here, we are talking about the Henry's law. What does Henry's law talks about? It's very easy, whatever you have just seen on the board. So it talks about when the temperature is constant. We are not talking about what exactly happens when the temperature changes. Let's keep the temperature constant, maybe the room temperature. The mass of the dissolved gas, how much gas, 1 gram, 2 gram, 5 grams, whatever we are trying to, dissolve in a given volume of solvent is directly proportional to how much pressure do we apply. The same thing that we were looking at, okay? The more pressure we apply, the more, particles of the gas, molecule, the gas goes inside the solvent. So this can be written as mass of the gas which is getting dissolved is directly proportional to the pressure applied. When we want a proportionality constant, mass is equals to Kp, where K is the Henry's constant. So do write H in the subscript. Do remember this, okay? Is this clear? And now, guys, pay attention. Whenever we're talking about the variation, so when we are increasing the pressure, the mass, this is M, not E. Don't get it confused by E. This is M. The mass of the gas, Mg, is increasing. Clear? Yes. And let's look for the another comparison between the other gases. So now at same pressure, this much mass is of helium which is dissolved, this much mass of nitrogen which is dissolved, and this much mass of oxygen which is dissolved in water. Now then, what do you think? Which one of them is which one of them is more soluble? Oxygen, nitrogen, or helium? So let's talk about the solubility. Solubility of O2, solubility of N2, and then the solubility of helium. It's clear, right? More mass of oxygen is getting dissolved. This is going to be the correct answer, right? Do write it down in your notebooks. And now let's talk about more. So ultimately, whenever we're going to talk about the statement, final statement, it says the partial pressure of the gas in vapor phase. The partial pressure of the gas, the pressure that the gas applies. So because you should know, whenever we're talking about the solvent, which is actually having the gas inside, does this gas tries to escape out as well? When there is no external pressure, will this gas try to escape out? Or maybe, just do one thing. As soon as you open up the cap of the Coca-Cola bottle, try to keep your hand on the top and try to seal it. See if you can actually, feel some amount of pressure. And when you remove your hand, you will feel it, okay, that there was some amount of more pressure which was applied by the gas from below. So, the gas molecules which are available in the solvent, even sometimes when they try to escape out, they apply pressure, okay, and that particular pressure is known as the vapor pressure. That is known as the vapor pressure, okay. Do remember that. And now, when we're talking about the partial pressure of the gas, that is again the vapor pressure, but in a different term. We'll talk about that. What is the difference between the partial pressure and the vapor pressure? Is proportional to the mole fraction of the gas. That means, pay attention guys, if in 1 liter bottle I have 1 gram of CO2 added, and here I have 3 grams of CO2 added, and I open up both the bottles, which one of these bottles will show more partial pressure of, where will you see more pressure applied by the gas? Because the outlet or the cross-sectional area is same. Where would you see the partial pressure of the gas more, which is coming out? Where the amount of CO2 is going to be more, because every second the number of molecules or the of CO2 which will try to escape are going to be more. A cold drink with more CO2 and a cold drink with less CO2, you will always see more CO2 coming up, correct? So yes, over here you guys are correct. Okay, Khushi is correct, Punarvas is wrong. So do remember this, okay? So this is what is said by this particular statement. Whenever we are going to look for higher partial pressure of the gas, the mole fraction of the gas should be higher, is what you have to remember. Then what's the role of, what should we know about the KH value? See, this KH value for at given temperature, this KH value changes for oxygen when the temperature changes. But if we're going to take the temperature constant, the KH value for a single gas remains constant, and this is what we're going to look for. Do you have to remember all the values on the table? No. But do you have to remember something? Yes, you have to remember a trend. I'll tell you. So let's talk about helium at 293 Kelvin, and then we have N2 at 293 Kelvin, and then we have O2 at 293 Kelvin. Same temperature. These KH values are found experimentally, and these KH values are given to you. You do not have to remember the KH values, but the KH value of the helium is 144 For nitrogen it's 76. For oxygen is 34. Do you remember that particular table, this graph? We saw that the solubility of oxygen is more, solubility of N2 is less, and solubility of He is much less. But when we talk about the KH values, so what we really see, the KH value for helium is more, nitrogen has less KH value, and oxygen has much less KH values. Always remember KH and solubility. Solubility of any gas is inversely proportional to the KH value. If the KH value is going to be higher for any particular gas, the solubility is going to be less. For 144, it's going to be very negligible. For 76, it's going to be slightly better solubility, and for 34 KH value, the solubility is going to be much more better. When we talk about even CO2, solubility of CO2 is going to be better than oxygen or lower than oxygen, is what you guys have to tell me in the chat. Come on. It's okay, Punarvas. Now let me know. Oxygen has a KH value at 393. There won't be much difference when we go from 293 to 298. So 34, and for CO2 it's 1.67. Let me know. Why there are two N2 gases? I'll tell you. That is all because of when you change the temperature, 293 and 303. When you increase temperature, solubility should be less, and when solubility has to be less, KH value will increase, right? Because they are inversely proportional. So when you increase temperature from 293 to 303, the KH value also increased, which means when you increase temperature, solubility decreases. Logical one, right? So now let's talk about the example, this example. N2 gas is bubbled out through water. So water is going to be the solvent, N2 gas is going to be the solute at 293 Kelvin. But don't worry about the temperature, because in such type of questions the temperature remains constant. How many millimoles of N2? What are we talking about? Moles. 10 raised per minus 3. How many millimoles? So x into 10 raised per minus 3. We have to actually look for, the exact answer. So now, gas would dissolve 1 liter of water. So the volume is given to you. Assume that N2 exerts a partial pressure of P. Write it down. P of 0.987. Given that the KH value, Henry's law constant value, is given to you as 76.48. KH value comes out to be 76.48. What will you calculate? Now guys, pay attention. The formula was P is equals to KH into mole fraction of N2. Let's have partial pressure of N2 upon KH value, where we are going to calculate the mole fraction of N2. Give me an answer. Give me an answer. So over here we have, write it down, on the numerator 0.987 upon 76.48. You'll get an answer, which is going to be the mole fraction, not the moles. You will not have the answer as moles. You'll have the answer as mole fraction. And now, you guys have to give me the answer over here. Okay? Then, when you are going to talk about the number of moles, the mole fraction of N2 has a formula. Number of moles of N2 upon number of moles of N2 plus number of moles of H2O. 1 liter of water. Guys, 1 liter of water has 1000 grams of water. And you should remember, number of moles for 1000 grams, 1000 upon 18, you get the answer 55.55. Okay. It's a general one. Every JEE and NEET student should know. 1 liter of water, 1000 grams, which is going to have 55.55 moles of water. Okay. And now, 1.29 into 10 to the power minus 5. Yes, absolutely correct. So I'll write it over here. 1.29 into 10 raised power minus 5. So guys, 1.29 into 10 raised power minus 5. Can I say this is damn negligible in front of 55.55? Yes, right? So I'm writing number of moles of N2 is too much lesser than number of moles of H2O. So over here I am going to neglect this. I'm going to write number of moles of N2 upon number of moles of H2O, and this is given to us, the mole fraction 1.29 into 10 raised to minus 5. Oh, by the way, I'm so sorry, this is not the moles, but ultimately as the mole fraction is not at all even close to 0.1 or something, that's the only reason we are neglecting it. Okay, so do remember that. And now ultimately this is given to you, and what is this? Number of moles of N2. This is what you have to calculate. Multiply 55.5 by 1.29 into 55.5 into 10 raised per minus 5. But this is going to be the moles. You have to calculate in millimoles. So do remember that. You have to multiply it by 10 raised to 3. Okay? So do remember that. Come on. Okay, on solving we are getting the final answer to be 0.71 millimoles. Yes, 0.71 millimoles is going to be the correct answer. Do remember this, okay? Yes or no? Khushi, you're doing absolutely correct. And I'm so amazed that you are actually doing each and every question with good amount of dedication and even doing it correctly. Amazing. Keep it up. And now let's talk about the application of the Henry's law. So whenever we talk about the application of Henry's law, so you should remember, I had been giving you this example since the starting of the class, the CO2 in the soft drink beverages, right? So ultimately, whenever we have to increase the solubility of the CO2, if you want more and more CO2, because I'll tell you something, what I feel is Thumbs Up is actually having more fizz than Coca-Cola, or even Appy Fizz is having more fizz than any other drink. Okay, I'm not comparing each and every, I'm just giving you a real life experience. So obviously, to make a particular beverage more fizzy, you have to apply more pressure while putting up the gas. Okay, so by applying pressure, you can put more amount of CO2 in the container. Okay, and when we are talking about the divers, we're talking about very painful phenomena which is known as bends. And what exactly happens over here? So let's say this is the this is the sea, and when divers gets inside, the diving, this is the sea level, and it's right now over here. What do they carry in their oxygen cylinders? I mean, obviously the oxygen, nitrogen. But when these divers used to only have oxygen and nitrogen, guys, let me know one thing. Oxygen, if it gets dissolved in our blood, will it get consumed? Yes. If nitrogen gets dissolved in our blood, does it has any role? No. But when the diver goes much more deeper, due to the pressure, due to the presence of water and too high temperature, pressure, what exactly happens? At too much depth, the nitrogen also gets dissolved in the blood, because when pressure increases, solubility increases. Correct? By the way, with the KH values that we know, solubility of oxygen is more than nitrogen, but oxygen will also get dissolved, and some part of nitrogen will also get dissolved, but oxygen will get consumed. Nitrogen stays inside the tissues, inside the blood vessels, and then what exactly happens? When the diver comes up, the pressure reduces, solubility of nitrogen reduces, and as fast this diver comes up, the nitrogen starts coming out of the blood vessels very quickly, and it gives a lot of pain, and then it can be fatal as well. So in order to make this less painful phenomena, what exactly happens? Instead of putting too much of nitrogen is there, but in very small amounts, helium is added. And why helium? Because when we compare helium and nitrogen, helium has very high KH value. KH value of helium is very much high. Or I should write it like, the KH value of helium is way much higher than the KH value of N2. and if the KH value of helium is too much high, the solubility of helium in our blood is going to be very less even at higher pressures. Okay, na? So do remember that. So ultimately this particular painful phenomena is avoided. So do remember that. How did you become moderator, Khushi? So guys, in order to become a moderator, one student has to be dedicated. One student has to come to the sessions regularly and stay till the end. Just like Khushi. Khushi comes to the sessions exactly in the starting and she stays till the end. She gives me a lot of answers. She talks, she learns. So it's not if a lot of students are coming just for entertainment, okay, you should have entertainment. But if I'm trying to give you best of the best knowledge on JEE, for JEE online for free, then this is the best thing that you should do. Okay. And now ultimately at high altitudes, partial pressure of oxygen is less. When we climb, when we are actually going to the hilly or the mountain regions, a lot of people, and when somebody is doing, climbing a mountain, even at that point of time, the partial pressure of oxygen becomes really low. And that's the reason the solubility inside the body, inside the blood becomes really low. And hence, then what exactly happens? Anoxia. Okay, na? Dizziness, lack of oxygen, feeling less energetic, feeling dizzy. That's what happens. It's all because of the partial pressure and the solubility. So do remember that. These all examples are actually going with the Henry's law. Okay, so do remember that. And now we are talking about the vapor pressure. So what is the vapor pressure? Vapor pressure is the pressure exerted by the gaseous molecules at the surface of the solution. It's here. So even if I'm going to keep a barrier here, and if I can say the gaseous molecules are available, how hard these molecules are pushing the surface. Could be hand, it could be any film, it could be any coating, whatever. Okay, so higher the pressure exerted by the gaseous molecules, higher is going to be the vapor pressure. If you would go by the definition, pressure exerted by the vapor molecules. Which vapor molecules? Above the liquid surface in equilibrium with the liquid at a given temperature is called vapor pressure. Because whenever we talk about the vapor pressure, and let's say I'm actually talking about a closed container, let's say, so if one gas molecule is coming up or particle is coming up, one would be going down. So it stays in equilibrium, but how much pressure? Will this film experience any pressure? Yes, that's the vapor pressure. Do we have vapor pressure when the bottle is locked? When the cold drink bottle is locked? Yes. So if you would see, if I'm making up soft drink bottle, okay, if the cold drink is still here and this is the cap, at this particular region, do we have gas? Yes, we do have, right? And which part of this particular, is the cap actually experiencing a lot of pressure? Yes. And as soon as you open up the cap, right, it happens, right? So that's a simple example of vapor pressure. So do remember that. Yes. And now let's talk about factors affecting the vapor pressure of the liquid. If we increase temperature, the vapor pressure will increase because more and more of molecules, more of the gaseous particles will try to escape out. Okay. So vapor pressure increases with the increase in temperature. So when I'm writing temperature increases, vapor pressure increases. Okay. Nature of the liquid. If the liquid and the gaseous molecules having good bonding, then not much vapor pressure. If the liquid and the gas hates each other, so ultimately the gas will try to escape much more easily, will try its best to escape out. So you do remember that. So if liquids which have weak intermolecular forces of attraction with the gas are volatile and have greater vapor pressure. So do remember that. Okay. If there are liquids which are having too much good amount of intermolecular forces between the molecules, then ultimately they stay together. Okay. But when the intermolecular forces of attractions becomes weak, the molecules try to jump up, get vaporized, and ultimately the vapor pressure becomes more. Purity of liquid. So pure liquid, whenever we talk about pure water, pure alcohol, they have vapor pressure higher than its solution. We'll talk about it. So guys, now pay attention. What I am trying to tell you over here is, let's say I have 5 ml of water, okay, and at any point of temperature, will the water vapors try to evaporate? Does water evaporate even at 40 degrees Celsius? Yes. Will water has its own vapor pressure? Yes, because when water molecules are going out, are becoming vapors, these vapors are going to have their own pressure. But now guys, pay attention. What exactly happens? So when we are actually having 1 kg of salt and I add the same 5 ml of water inside, okay, and I mix it pretty much well. Now do you think in the second case water vapors, there would be a tendency of forming of water vapors, or in which scenario do you think there is more tendency of becoming, having water vapors? Do let me know. The option 1 or the option 2. I'm keeping it both of them under the sunlight. In which condition do you think the evaporation of water is going to be more? So sir, can we take an example of green algae which grows on water surface and kill the fishes and the aquatic organisms? Yes. If you're talking about such phenomena, then ultimately you should remember that actually happens because, I'll tell you. So if this is the pond or a lake and this is water, and on the water, if all the surface is covered by the algae, then ultimately it has blocked the contact of air and water. So ultimately you should remember, sunlight falls and algae grows, and algae spreads over the pond. But when it comes, and there are fishes, see, this is one fish, this is second fish, and fishes have already consumed all of the oxygen that they had, okay. Now as the algae is actually present on the surface and oxygen, there is no supply of oxygen or the air in direct contact with water, then there is no point of oxygen getting dissolved in water, and hence fishes starts dying. So ultimately, yes, you should remember, in a condition where we have pure solvent, here the vapor pressure is going to be more, rather than comparing, if we are talking about any of the solution, okay. So do remember that. We are talking about non-volatile. When solution is with non-volatile solute. Non-volatile solute has no vapor pressure. So let's talk about the sugar, salt. Do they form vapors at 40 degrees Celsius? No, right? So they do not. If they do not have vapors, then they do not have the vapor pressure. Vapor pressure is the pressure exerted by the vapors, okay. So you should have vapors for having vapor pressure. Do remember that. And now let's talk about effect of adding solute. When a liquid contains a solute, some of the solvent molecules are replaced by the solute particles. So I'll talk about this. So let's say this is pure solvent. So in the case of pure solvent, solvent is made up of molecules. So making up molecules. On the surface there would be molecules occupying the space. But when we add solute, and solute is homogeneously mixed, so it will be present everywhere. It will be present here, everywhere. When we say everywhere, then why leaving the surface? So can we say when the solute particles are occupying the surface as well, can we say the solvent particles which were already there, now the numbers have decreased? Because some of the solute particles are actually occupying the surface. Yes, and then when we are talking about the red ones, these are non-volatile solutes which do not form vapors. And when we talk about the yellow ones which are volatile, which can form vapors, then as the number of volatile particles have decreased on the surface, earlier every particle was allowed to become, vapor, but now it has decreased. So the vapor pressure is going to decrease. So do remember this. I think salt have high boiling point around 1400 degrees Celsius. Yes, absolutely correct. Correct. It has a boiling point, but what about at 40 degrees Celsius? No vapor pressure, zero. Okay. So do remember that. Sir, then why can't aquatic plants provide oxygen to fishes? It's a good question, right? Even not aquatic plants, even algae. The green algae does the very efficient amount of photosynthesis. But the point is, if the fishes are more and they are consuming, let's say 1 liter of oxygen per second, okay, and the algae or the plants, underwater plants are actually providing oxygen at a very slower rate. First of all, under oxygen plants not all provide oxygen, but let's talk about algae. But algae is only able to provide 0.2 liters per second of oxygen. It's a supply and demand game. If the demand is more and the supply is less, fishes will choke, right? So do remember that. Okay, is this clear? So initially when there was no solute, what was the scenario, guys? Pay attention. Okay, I'm gonna make it again. When there was no solute, I have to change the color as well. Yes, this is how it was, and each solvent particle was allowed to vaporize. But when we talk about the addition of solute, non-volatile solute, the number of particles which are eligible to become volatile on the surface decreases, and hence vapor pressure decreases. Okay, so do remember this. Yes, and now this is what we are talking about. So when we are actually having a example where, let's say, this is the solvent particles, when there is no solute added, you see more number of solvent particles in the vapors, and as soon as you add a non-volatile solute, less number of particles are available in the gaseous phase. Can you see the difference? More and less. That's what we're talking about. It's there on the text. I'm not going to go through the text for you guys. You can definitely go through it whenever you are going through the PDFs. And now, ultimately, we're talking about the Raoult's law. So Raoult's law talks about the vapor pressure of the solute, the vapor pressure of the solvent, and then the vapor pressure of the solution. Okay. So now, guys, pay attention. So now, ultimately, everything is happening at given temperature, because when temperature increases or decreases, pressure changes. So we'll stick to constant pressure. The vapor pressure of a solution obtaining non-volatile solute is directly proportional to the mole fraction of the solvent. So now, let me know something which is going to have higher vapor pressure. I'm putting up 100 grams of water. Okay, and I'm actually adding 10 grams salt, and in the other case I'm adding 100 grams of water, but I'm actually adding 30 grams of salt. Which container number B, container A, which container is going to have more vapor pressure? Come on, guys. Abhirami, very bad. Where were you? Left the class. I told you, right? The class will go for longer. But anyhow, guys, do let me know. What do you think? What's going to be the scenario? We are going to cover solution chapter in 3 classes. The reason is I want all of you to have the syllabus covered before examinations. So now, guys, let me know. And do you see I'm going in so much details, so much examples. That's where the class is going to be longer. Now, the correct answer to this question is the vapor pressure is going to be more in the option A, where the quantity of solvent is more, you know, when in comparison. So ultimately it's the mole fraction that we're talking about. So over here the mole fraction of the solute is less, over here the mole fraction of solute is more, correct? And when the mole fraction increases for the solute, the mole fraction of solvent decreases, right? So over here the mole fraction of water is more, and over here the mole fraction of water is less. That's what we're talking about when we talk about the Raoult's law. So Raoult's law is saying, if you are actually having mole fraction 1, mole fraction 1 means pure solvent, nothing is added, pure solvent, then this point, if on the y-axis we have pressure, vapor pressure, this is going to be known as the PA naught. Naught tells us that it's pure, the solvent is pure. A stands for solvent, okay, B stands for solute, okay, so do remember that. So this is the point where we have the maximum vapor pressure at a given temperature for the solvent. And now when we are decreasing the mole fraction of solvent, when we are going to decrease the mole fraction of solvent, ultimately we are increasing the mole fraction of solute. We are adding more and more of the non-volatile solute. And similarly, what do you see? The solubility is, or the vapor pressure is decreasing. Now pay attention. If you talk about this one, 0.8 mole fraction of solvent is 0.8. You know, the vapor pressure decreased. Mole fraction of solvent is 0.4. The vapor pressure is decreasing. What if there is no solvent available? Only and only pure non-volatile substance. By the way, you clearly do not have an idea in which stance I'm sitting. See, this is how I am. So you do not have an idea how am I standing. But you know, that's the best part of teaching online. You know, students do not know in which particular, you know, position sir or ma'am is standing. Now, guys, pay attention. Ultimately, what if I am talking about 0 mole fraction? 0 mole fraction of a solvent means that the solute is actually 100% available. There is no amount of solvent available, correct? And when we are talking about a non-volatile solute, just like, you know, sugar or the salt, do we have vapor pressures? No. That's the reason the vapor pressure is also 0. Is this clear? So can you give an example of pure solvent? Come on. 100% water, 100% ethanol, 100% benzene, 100%, you know, any solvent that you know, any solvent that you know, okay? I mean, just remember that. Any liquid, you can actually put it over here. Okay? Understood? Amazing. Now, yes, so the formula. Guys, if I want to know the vapor pressure at 0.8 mole fraction, when the mole fraction is 0.8, what is going to be the, you know, so if the vapor pressure, we are going to write PA is going to be equals to mole fraction of A into the actual one. So now do remember, when the mole fraction is going to be 1, then the vapor pressure and, you know, the partial pressure and the vapor pressure is going to be same, correct? So now guys, pay attention. When we are going to talk about the vapor, let's say the mole fraction is 0.5 and we know this value experimentally. Let's say this is 100 mmHg. This value is going to be 50 mmHg. So I'm talking about something over here. This is going to be your answer. So this is a very simple particular equation which we have written in graph as well. So guys, now pay attention. So now ultimately you should remember this over here is PA naught. This is the intercept. This is the intercept actually. And over here what you should remember is that it has a slope. And you should also remember that ultimately whatever answer that you guys are going to get, that is going to be the vapor pressure that we are actually writing as PA. PA naught means pure, 100%. When we talk about PA, it's impure. So do remember that. Okay. And now let's move ahead. Yes. So now what are we talking about? When we're talking about liquid A and liquid B, when there are two liquids, and liquids are volatile, ठीक है ना? At some higher temperature we can make them gaseous. So when we're talking about liquid A and liquid B, both of them would be having their own vapor pressures when they're pure. So now guys, pay attention. Okay. So now I'm writing over here pure B, and over here I'm writing pure A. Clear? Does pure A solvent, one of the liquid, will be having its own vapor pressure when it's pure? Yeah, right. Okay, this is going to be the one. So I'm writing PA naught. Will the liquid B will be having its own vapor pressure? Yes. It could be more or less. So I'm going to just make it here. This is going to be P naught B. When the mole fraction of B is 1, what is going to be the mole fraction of A? You guys have to let me know. Then in this scenario, the mole fraction of A is going to be 0. Over here, when the mole fraction of A is 1, mole fraction of B is going to be 0. Clear? When something is pure, then there is no point of having B. There's nothing, nothing will be B. Now, what is going to be the scenario? Guys, pay attention. Just join these lines, join these points. Okay? Though you are able to see way much less difference, I'll make it again. Okay? I'm writing PB naught over here. Now make it. Okay? So now guys, pay attention. What if the mole fraction of A comes out to be 0.5? What will be the mole fraction of B? Again, yes, 0.5. So we're talking about something over here. When the mole fraction of A, see, mole fraction of A decreases from right to left, and mole fraction of B decreases from left to right. So when we're talking about mole fraction of A and B is equals to 0.5, it is going to be in the middle. What is this? This is going to be a vapor pressure. You will be able to see some value. This value is the vapor pressure of the solution. This is the total vapor pressure. Now pay attention. It is higher than P naught B. Why so? Because we have mixed another component which is more volatile. And this particular point, this vapor pressure is lesser than PA naught. Why so? Because PA naught has been mixed with something which is having less vapor, vapor pressure. Getting it? When there is a kid, when you are the one, and there is a team forming up in a school where two kids have to pair up for a project. One kid has too much high performance. He or she can complete its file or whatever experiment within 2 days, right? And another kid takes 5 days. Then ultimately, when both of them will work together, can we say that the project will complete within 2 days? No, right? The one which is more efficient will try its best to bring up the one which is less efficient to work with him or her, and then ultimately they will finish the work within some, between 2 or 5 days. You're getting the point? That's what's happening over here. So this is this point over here. This one is going to be the vapor pressure of solution. We are going to talk about this. Okay. So now, because the pressure exerted by A is directly proportional to mole fraction of A, right? So do remember that. This is the one. PA naught into XA is PA. PB naught into XB is equals to PB. Correct? This is what we are talking about. Now, when we talk about total pressure, this is for solution. This is for solution. That is what I'm trying to tell you. Guys, Mole fraction of A is kept 0 over here. So mole fraction of B is kept, so B over here is 100% pure. A over here is 100% pure. Could be, ethanol and water. And now this is the vapor pressure of water. This is the vapor pressure of ethanol. Whenever we are going to, have any mole fraction for them, you will get the total pressure, which is going to lie somewhere here, or somewhere in this line. This line, it will always be on this line. So it could be this much, this much, this much, this much, this much, depending upon what mole fractions of both the components you are having. Do remember that. Also remember, no two components will have mole fraction something like 0.8 and 0.8. No, because you should remember, mole fraction of A plus mole fraction of B is going to be 1. The sum should be 1. So 0.5 and 0.5 is possible. 0.6, 0.4, 0.7, 0.3, something like that is always going to be possible. Okay? Yes? So do remember that. So this is the formula. And what is PA? PA is vapor pressure of pure solvent into mole fraction, vapor pressure of pure solute B, and the mole fraction. Ultimately, you should remember this can be written as 1 minus XB, and then multiply. So PA naught into 1 is PA naught into XB minus, and then PB naught, but positive XB, PB naught. Taking XB on common, you get XB outside. So I'll do it once for you. So PA naught minus P naught XB plus PB naught XB. Now take XB common. This is what happened over here. Okay? Yes or no? Do remember that. And now we're talking about liquid solution. We're talking about only two component system, which is binary solution. There are ideal solutions. These ideal solutions obey Raoult's law. These ideal solutions obey Raoult's law, what we have seen. This graph will be obeyed. This particular formula is going to be obeyed for total pressure. But when we talk about the non-ideal solutions, these solutions disobey Raoult's law. Do remember that. Okay? I'm writing few things for you. Delta H, when we mix both the components. So when we mix both the components, does the energy gets released or it's an endothermic? No, it's 0. Does the volume changes? No. Okay? So do remember that. And why does this happen? Because whenever we talk about the ideal solution, which is following the Raoult's law, if there is an interaction between molecule A and A, and if there is an interaction between the molecule B and B, will they love each other? There would be van der Waals forces or other forces. Yes. Will they love each other? Yes. So the loving between A and B is also going to be same. The interactions, I'm writing it again, AA interactions and BB interactions are similar to AB interactions. Okay? Do remember this. And now, this is the one which I have told you. Same graph, just the concept is getting repeated again. We are talking about the interactions over here. I've told you this. Delta V of mixing. So let's say in the case of ideal solution, I added 50 ml of a particular component A and 50 ml of component B. How much will be this? What will be the volume of the solution? 100 ml. Okay, I'm writing it over here. 50 ml plus 50 ml, you will get 100 ml. Okay, and when we talk about mixing up both the things, ultimately there is neither heat released and neither heat consumed. Okay, neither there is energy taken. So hence delta H of mixing remains the same. And when we talk about the non-ideal solutions, so they do not obey. They do not obey. It's not equals to. So do remember this. So ultimately, whenever we talk about the non-ideal solutions, when we mix them, there is a difference. When we mix them, there is a difference in volume and there is a difference in energy. We'll talk about these. So there is one which is the positive deviation. In the case of positive deviation, do remember this, and you guys have to let me know. A and A interactions, they love each other. B and B also loved each other, but A and B don't love each other. Will they fight? Yes, obviously, right? Why are you close to me? Go. I was about to say go somewhere else, go to hell, है ना? Something like that. And now when we're talking about B saying it to A, same to you, back to you, no return, something like that, it will happen. Now you should guys remember that whenever we're talking about A and B, they will repel each other. The interactions are not great. They're not loving each other. Wow, you're here, I didn't know about you. They are going to repel each other, right? So ultimately what exactly happens? If this is a solution, okay, where this is component B and this is component A, will A try to push B upward? If this is B and this is A, or let's say this is A and this is B, will these molecules or particles try to push each other? B will be like, go away from this particular solution, I don't like you. A will be like, you go away from the solution, I don't like you. Yes or no? So as they do not like each other, the molecules which are actually present will push the another molecules out. Okay, and in this scenario, the tendency to form vapors will become more. This solution will make vapors much more than what AA or BB could make. And in such scenario, the vapor pressure increases. So ultimately, what we were expecting, if the mixture would have been ideal, they would be following this particular line for the total pressure. But in actuality, whenever we calculate their own total pressure of the solution, it is always higher than what was expected. So if the mole fraction is 0.5 and 0.5 somewhere here, and you were expecting the vapor pressure of the solution to be like this much, right? It is coming out to be way much higher. Okay, getting the difference for the ideal solution? But as it is not an ideal solution, you will have a vapor pressure which is going to be higher. So do remember this. Clear? Now let's talk about something else. And ultimately you should remember the delta V is positive. Now if I add 50 ml plus 50, it is gonna become 1.101. Do remember this. Okay? Boys and girls, do remember this. I mean, not exactly, but I'm trying to give you an example. Because in the mixture, B and A are pushing each other. The intermolecular distance is going to be more. Intermolecular distance will slightly become more. 50 and 50 ml will give you a solution of more than 100 ml of solution. Clear? So do remember this. And when we talk about delta H of mixing, you will try to mix them. They'll say no, we don't like them. I don't like A says I don't like B. Then you have to provide energy. That's the reason it becomes an endothermic process. Do remember that. And now let's talk about the negative deviation. What exactly happens? When we talk about A and A, they were loving each other. When we talk about B and B, they loved each other. But when we talk about A and B, they are very happy with each other. Okay? Are you guys getting the point? They were happy. Okay, good. But when they met each other, they are super duper happy. Then what's going to be the scenario? if let's say this is the component B and if this is the component A, and I'm trying to heat, what will A say to B? No, I will not let you go. Okay, I love you so much or whatever shit, है ना? Okay, but yeah, something like that. A and B, don't go, please. And even I'll try my best, so that you don't vaporize and something. And even that is going to happen with when A is at the top and B is at the bottom. B will also try to keep it much, closer to itself, right? So in such a scenario, even when we are trying to provide temperature, they are not trying to go away. Give me a second. Oh, by the way, एक second. It's a positive deviation wala thing. I'm so sorry. I have to change the slide. I got carried away. It's a positive deviation wala slide. There are the examples. I'll tell you the examples for positive one first. Okay. So ethyl chloride and water. Because when water plus water are present, they have hydrogen bonding. Do they like hydrogen bonding? Yes. But when we talk about ethyl chloride and ethyl chloride into 2, these have van der Waals forces, good amount of van der Waals forces, better than water. Why so? Because ethyl chloride is a heavier molecule than water. Heavier the molecule, better is the van der Waals forces. So when water and ethyl chloride is available, ethyl chloride is saying, if I would have been there with another ethyl chloride, we would be having good van der Waals forces. And water is saying, what are you saying to me? Look at yourself. When I was with another water molecule, I was having much better hydrogen bonding. Can you give me hydrogen bonding? No, right? So now water is not getting a good amount of hydrogen bonding, and neither ethyl chloride is having good amount of van der Waals forces, and that's the reason they're fighting. Okay, and now we are going to talk about the negative deviation as well. Okay, so now in the case of negative deviation, again I'm going to write it. AA interactions are good, BB interactions are also good, but when A and B meets, they are delighted. Okay, and then over here what you should remember, same thing. If this is A and this is B, they're not letting each other evaporate much easily. Okay, they're holding each other. I won't let you go, making promises and all. And then ultimately, if you keep the mole fraction, let's say 0.5 and 0.5, you are expecting them, according to the Raoult's law, that they will be having this much vapor pressure. But in reality, they're having this much vapor pressure. Or maybe, yeah, this much. Getting the point? So it is way much lesser than what we were expecting, theoretically, according to Raoult's law. And when we keep A and A 50 ml, when we keep B and B 50 ml, and we add them up, A and B is going to be 98-99 ml, because the intermolecular distance decreased because of more affection that they're getting. So do remember this. Is this clear? Amazing. So this is what you have to remember. So in the case of negative deviation, negative as the word says, make a curve which is lower. And in the case of positive deviation, make a curve upper. So do remember that, okay? It is going to help you in board's examination as well. And now you should remember the delta V of mixing. After mixing it up, the change in volume is going to be negative. 50-50 should be 100, but ultimately you're getting 98. So it is going to be negative. What about the delta H of mixing? When two things love each other, the chemistry, the molecules, then ultimately they will only do it when they have much better stability. When A and A was there, B and B was there, okay, they were happy. But when A and B got mixed, they got super happy because stability increased. When they are feeling more stable with each other, then ultimately you should remember they release a lot of energy, and hence this becomes exothermic. Do remember this. Okay? Yes. And few examples. So ultimately we will talk about the chloroform and acetone. I'll tell you why. So whenever we make acetone, make it like this: carbon double bond O, CH3, CH3. Okay. And now let's talk about this. This is partially negative. This is partially positive. Okay. When this acetone is with the another acetone, these are going to have dipole interactions and even van der Waals forces. Okay. But now guys, pay attention. When we are talking about the chloroform, how does chloroform looks like? So it is going to be carbon, chlorine, chlorine, chlorine and hydrogen. When one particular chloroform is with the another one, give me a second. Carbon, chlorine, chlorine, chlorine. So this is partially negative, partially negative, partially negative, and then ultimately this is going to be damn partially positive, so something like this. So there are again dipole interactions, van der Waals forces are available. But when this particular hydrogen, which is damn partially positive, and when they meet partially negative oxygen, then acetone and chloroform finds hydrogen bonding. This is a special case of hydrogen bonding. Hydrogen which is connected to carbon is not really eligible to form hydrogen bonding. It is only possible because of the minus I effect. You guys are class 12 students and I am assuming that you know the minus I effect. Okay. So minus I effect is there. This makes the this particular hydrogen too much partial positive and hence becomes eligible for forming or for showing hydrogen bonding with the partial negative oxygen. So initially when acetone and acetone was available with each other, no hydrogen bonding. When chloroform was with each other, no hydrogen bonding. But when chloroform and acetone met each other, hydrogen bonding. Wow, they never knew this. So ultimately this shows negative deviation. So do remember that. Okay, is this really clear to each and everybody? And now this is what we are looking at: partially negative and hydrogen partially positive, acetone, chloroform. Do remember this. Amazing, right? Now, yes, azeotropic mixtures. So we will talk about the azeotropic mixtures. So azeotropic mixtures are the two, the mixture which is made up of two components, but if the presence of one and the second component is absolutely precise enough, it's not available for each and every concentration. It should be very much same. So ultimately, even if we try to boil it and distill it, we are not able to separate it. So what exactly happens, I'll tell you in very vague scenario. So let's say you have a particular distillation chamber. So ultimately this is going to be a flask which is kept over tripod stand, and you are putting a flame. Ultimately you are having water and you are having just 5% alcohol in this. You want to make this water as much free from alcohol. What will happen? You will boil it up. Which boils first, boys and girls? Water or alcohol? The alcohol boils first at 78.4 degrees Celsius. Water boils at 100 degrees Celsius. Now pay attention. Alcohol starts boiling, and what temperature are you going to keep? 80, where only alcohol boils rapidly, but water does not. So what is, which particular molecule is going to be there more in the vapor phase? The alcohol. And then ultimately you condense it, you cool it from here till here through cool water. Okay, externally you can have water coil, okay, cool water running, and then you are actually condensing up the alcohol. So in the different flask you are going to have liquid alcohol available. Here the percentage of the alcohol is going to be more, and ultimately over here the percentage of water will become more. So something like that. Okay, but when we are trying to distill the azeotropic mixtures, this does not happen, and this only happens at some particular percentage. So we're talking about if we are having 95.57 alcohol percentage, and if we are having 4.43% of water by mass, weight by weight percentage is what we're talking about, then you should remember, when we are doing up the distillation, same thing. If we are trying to get it from here till here, the concentration was 95.57. Here also the concentration is going to be same. You will not be able to remove it. So what you can do, you have to first of all change the concentration. You have to change the weight by weight percentage. Then only you will be able to do something. So, okay? This is known as minimum boiling azeotrope. Such azeotropes which is available in which the boiling point of the mixture becomes lower. 78.4 degrees Celsius. This is 100 degrees Celsius. But the temperature of the solution, boiling point temperature of the solution becomes 78.2. So do remember this, okay? Billu is actually making noise. Are you able to hear Billu? Billu is like, it's been too long. It's 11 o'clock somewhere around. Now come out. It's my time. Are you able to hear Billu? Come on everybody, let me know. And we will get Billu inside, okay? Acha, he's making some noise. Let me just get him. Let me just see if he comes up, okay? How many of you wants to see Billu? Meow. Wait. Come inside. Come. पकड़ लिया. Meow. Okay. He makes my t-shirt white. See? How old are you? Who's गंदा बच्चा? गंदा बच्चा कौन है? Good. So yeah, let's come back to the session. Go back. Bye bye. जाओ. Go. Don't be angry on me. He's actually angry right now. He wants my attention all the time, and probably he can't live without me. Something like that. You know, Billu and me are the example of negative deviation. Okay. So now let's talk about the minimum boiling point azeotrope. Okay, minimum boiling azeotrope. So the solution, the boiling point of the solution decreases. It was 78.4 for the individual ethanol, 100 for H2O. It's not in the middle. It's not 80, 84, 85, 90, 95. Not like that. It's 78.2 degrees Celsius. All because of the love and affection, the negative deviation. Ethanol and water is an example of negative or positive is what you really have to tell me. Okay. And now, ultimately, let's talk about the maximum boiling azeotrope. So guys, also remember, when we are actually having a solution where the boiling point decreases, that means they both are pushing each other. They both are pushing each other. No, you go first. You go first. And in such a scenario, the boiling point of the solution decreases. Okay, so do remember that. And now, when we talk about the maximum boiling azeotrope, over here, these show negative deviation. Okay, earlier one, the positive deviation. And then ultimately, for my parents, I am their pet. Yes, it happens. So H2O 20%, HCl 80% by mass. So if you would see the actual boiling point of HCl and water, but now if you're talking about the percentage 20 and 80 of HCl and water, in this solution, the boiling point is going to be higher. Okay? It's somewhere around 108 degrees Celsius. So do remember that. Okay? Which is higher than the boiling point of HCl and water. So this exactly happens when we are talking about the maximum boiling azeotrope is what you have to remember. And if you have any doubts, we are actually at the end of the session. If you have any doubts, I am always going to be available on Telegram. So do join my Telegram channel and you can actually ask unlimited doubts and whenever you want on Unacademy app. Also, you will get the high quality video messages in English and Hindi as well. But what you really have to do is you have to send your doubt as clear as possible, one doubt at a time. Let us know the subject and just simply wait. A lot of students have already asked such doubts, even what you would be asking. So we have all the solutions ready. So do remember, it is going to be quick enough, and yes, just wait for it. Crop it properly. It should be clear enough. Tell us which particular particular subject you're asking from, and it will always help you. Make sure that the images are clear. No, much questions. Multiple questions shouldn't be there in one particular doubt. All the options should be visible. All the hints, all the A, B, C, D options should be visible in the question as well. Sir, I gave a homework. Yes, like yesterday. Okay, give a homework like yesterday. I have given it, you know, in the middle of the session. What was it? I gave you a question regarding. I gave you, yaar. I'm forgetting. I gave you a question which was about. I'll let you know in the Telegram group. Okay, and yes, subscribe to the channel, share it as much as possible, boys and girls, because with your share a lot of students, new students would come to this channel, and it will be really amazing to teach more and more of students like you for free, because the only agenda over here to teach on YouTube is to teach maximum students for free. Okay, so do that. Bye bye. Use this code whenever you are actually getting into Unacademy subscription. Do not forget that Spark and the Shine batch have really started for 2022 and 23 students, where all the teachers are teaching in English. Have you started teaching recently? Not really. I haven't. It's been long now. Yes, I do have an experience of 2 years plus, which is going right now, and we will teach more. Okay, chalo. All the best. Take care. Stay safe. Bye bye. Take care. Good night. And I'll be keeping up the classes longer. But though it had become 2 hours 15 minutes, I'll try to keep it within 2 hours. But yes, we will be covering up the syllabus on time. All the best. Take care. Bye bye. Tata. Good night.